I'd like to record a very short video for you guys about terminal voltage and what happens inside a battery effectively. So far we've talked about batteries, briefly about what a battery is chemically, and then also we've talked about them as ideal perfect voltage sources. I hinted earlier that batteries aren't quite the perfect voltage sources I implied they were because of some internal problems. This is the point where I want to actually show you what the internal problems actually are. For a fresh new battery, this is not going to be a major effect for the most part, but it is worth considering. So consider our perfect battery. Okay. In reality, every battery isn't really just a voltage source, though. There's always some internal resistance. So I'm going to put a little internal resistor in here, little r. And let's consider, this is really the battery now then, like that. Okay. Let's consider adding it in a circuit with another regular resistor, capital R. There will be some current I. Let's think about what happens here. Well, we know from Kirchhoff's law that, the loop law, that plus V minus I big R minus I little r equals 0. Okay? Or V is equal to I times big R plus little r. Or then again, if you prefer, V over big R plus little r is equal to the current. Now, if little r is a lot less than big R, this is basically the same as if it weren't there. It is close to V over R equals I. Okay? However, if the load, the big R here, is not big compared to R, in fact, even if it's smaller than little r, this starts to matter, this internal resistance. Okay? The way it manifests itself effectively is that it looks like there's a voltage drop across the battery. So I'm going to go back and draw again. Here's my battery. Okay. Here's the perfect battery, that's the voltage source. Here's the resistor. And here's the current going over it, big I. Okay. Well, if I actually put some leads across here and measured the voltage, what would I get? Well, I would get V minus I little r, okay? Now again, the I is potentially pretty close to what you would expect, and this may not be a very big effect. We might have V, big V over R plus little r times R. Okay, if big R is a lot bigger than little r, this is actually a pretty small number. This ends up being 1 minus R over big R plus little r, which is, if again, little r is a lot less than big R, this is pretty close to 1. And you get the exact voltage that you should get. But once little r approaches big R, okay, suddenly this fraction becomes important. For instance, if big R and little r are equal, we've got R over R plus R, that's R over 2R, that's 1/2. The voltage is dropped by a factor of 2. We've only got half of that voltage in the battery that I should have. At this point, the battery is probably well on its way out. And in fact, this is how you tell if a battery is dying and any electronics you have that are good about warning you when your battery's about to go. Smoke detectors, for example, are often very good about starting to beep when they realize the battery is starting to die. Use that last remaining juice to alert the people that, it's time to go ahead and change things. Okay. There is other ways to simplify this, by the way. I could say that the voltage measured is actually V times big R plus little r minus little r all over big R plus little r, which is the same as R over R plus little r, okay, times V. Okay, so what V measured is V perfect times big R over big R plus little r. And again, if big R is much bigger than little r, this is basically R over R, it's just 1. Okay? But as this gets bigger, or as little r gets smaller, this starts to matter. What I mean by little r or big R getting smaller, by the way, is if I have a load outside the circuit that's not very big, I've got very little resistance in it, this will also be an important effect, basically. But if most of the resistance is outside the battery, then what this basically says is, don't worry about the internal resistance of the battery. By the way, this can actually do some really weird things. If I drive current backwards across the battery somehow, and I can do it, okay? I can set my battery up, have my perfect battery here. By the way, what's really going on here doesn't really matter what order big R and the voltage source really are. They're actually all mixed together inside the battery, but we draw them this way typically. If my current's going this way, the voltage measured across is V plus I little r, which is really weird if you think about it. Okay? But there's actually, what this is saying is a bigger voltage across the battery than I'd expect. But the current's also going backwards from what I expect. So I'd have to have some external voltage source attached to the ends here, forcing current backwards down it. There are situations where that happens, that when I'm recharging a battery, if this were rechargeable, this would actually happen. I would actually have a bigger effective voltage across the battery than I would have expected. Okay, that's terminal voltage. I believe that appears in some of the homework problems of the week, so hopefully that's useful. And hopefully it gives you a little more insight as to how batteries work. Okay, I will see everybody in class.